Okay. So the topic of my presentation today is to make our Texas A&M community aware of some of the work we do in nuclear engineering towards a digital twin. And in the present case, we're working towards a digital twin for radiation source, accountancy, and control. I'll tell you in a few seconds what that means. My name is Jean Draguza. I'm a professor in the nuclear engineering department, and this is work done with a grad student, Ian Halvik, Jan Vermaak, Tom de Guire. Most of the results here are generated by Ian, and we have external collaborators, the DIMAC team from Los Alamos National Lab. DIMAC stands for Dynamic Material Control. Okay, so going to the next slide. What did I do? Okay, it's working. So I'll give you a little bit of background on nuclear material control, nuclear material accountancy and control specifically. Some background on the radiation transport equation. This is the equation we solve to determine where radiation is in a domain. I'll explain briefly why we need surrogate models for that equation. It's a little costly to solve. And I'll discuss inclusions or how to incorporate a surrogate model or reduce order model into a digital twin and bring some outlook. We've only been working on this for maybe 4 or 5 weeks. So our version of digital twin is a little rudimentary. You'll see this towards the end of those slides, but I hope you'll still enjoy it. So background, monitoring nuclear material is integral to the safe, secure, and efficient processing and management of nuclear material. Basically, you want to always make sure that you know where your nuclear material is. You want to account for every gram of it or dozens of grams or fractions of grams. And so at Los Alamos and at other places, sometimes production facilities have to be shut down or put offline for a period of a few days or weeks to do what people call a material inventory. You need to make sure that whatever came to your facility, whatever left your facility, and whatever is still in the facility, you have balance. So they have balance areas, and then you need to basically make sure that all material is accounted for. And of course, it's not always possible. You can have material unaccounted for. It could be holed up in pipes, could be in a form of not power, but powder or dust. And whether how much you deviate from an estimated or a target value by some sigmas, you can reach a warning or alarm limits, and you need to make sure that you know where your material is. The fact that you have to slow down or shut the facility for several days is actually quite costly. And they don't want to, it would be nice if we could do this in a dynamic manner. And hence the idea of basically monitoring basically live where the material is constantly through a digital twin. So they have a project called the DIMAC project, Dynamic Material Control, where they want to enhance the manufacturing agility of their production place and to optimize nuclear material accountancy and control. That's NMAC. I may use NMAC a couple of times here. So nuclear material may decay and emit detectable particles. This is how you can do material control and accountancy. Here we are interested in spontaneous fission from fissile material. So in the table here, you can see that there's a certain number for some isotopes, a certain number of neutrons that are emitted per second per gram of material. And if you have detectors, in this case, neutron detectors placed, you can basically detect radiation that is emitted from spontaneous fission from that material that you want to account for. And based on the detector count rate, you may determine the source strength of the material and its location, and therefore you may be able to account for how much material you have in your facility. The detectors we use here are just helium-3 detectors. You have a picture below. What kind of material fabrication rooms and facility we're looking at? So here are some examples from an public report. You can see that basically we're talking about rooms where processing, characterization, production, modification of materials are being performed. And you want to make sure that going from one room to another or going from one glove box to another glove box in a given room, you always account for the material you have. You always know where it is and how much of that material you have. And if you modify it, if it gets split into different forms or components, that you keep track of all of those. So those are complicated facilities. But we start with a simpler prototype room. So in this room, that's the top view. We have glove boxes that you can see, narrow one and wider ones, and you can see what kind of looks like pink squares. Those are actually helium-3 detectors, neutron detectors. You have 4 of them at the corners of each of those glove boxes, so 16 detectors. And by knowing what the detectors record, you may infer where the sources are inside your glove boxes. So here's a picture of the room. Highlighted are the helium-3 detectors. Those are the glove boxes in which we would put radiation sources, and we hope that the detectors will be able to, the count rates in the detectors will be able to infer from them where the sources are. Here's another view of that room at a slight different angle, so you can see what it looks like, and even a more close-up view where you can see the helium-3 detectors placed at the corner of the glove boxes. So we want to use a digital twin for nuclear material accountancy and control. So a digital twin, I'm sure that this morning and already on the website, people have given definitions. So here I go, like everybody else, I give a definition. So digital replica of a living or not living physical entity, and a digital twin should integrate the Internet of Things, AI, machine learning to create living digital simulation models, and a digital twin learns and updates itself through sensor data, for example. So in terms of nuclear material and accounting, what do we want the digital twin to be able to do for us? Well, we want to do the following things. We want to unfold the detector count rates into, so what the detector sees from what the measured values. We want to know where the sources are, so the location of the sources and the strength of the sources, and also how many sources do we have? Do we have 1 sources, 3 sources, 36 sources? We want this to be determined. And from the it is an echo or something. I don't know if you can fix this. And from knowing the source strengths and their position, we'd like to infer material balances in each compartment. We should, of course, include uncertainty quantification when we do this. We want to do this on a time-dependent manner, maybe every 5 minutes or every 10 minutes. We have an update of our material balance, and we want the digital twin to help us detect anomalies and raise flags whenever it's needed. So the inference process would be basically as follows. We have measurements, and we want to have a model that tells us where the sources are, that's the position R, what is the source strength, that's the value S, and how many sources we have, and we want to find the optimum solution to this problem, subject to some constraints, like the sources are in the glove boxes and not elsewhere, for example. So here's an example of inference that our colleagues at Los Alamos have given us as a demonstration. So you're able to find locations of sources into 4 glove boxes. But the question is, what kind of model should we really be using to do this inference? We can be purely data-driven. We run some experiments in the facility itself, and we learn from where the sources are placed during our experiments. We learn what the detector count rates are. And basically, it's entirely experimental data-driven. We run, learn, and use values. Of course, you could be doing this with simulations instead of running an experiment that can be either expensive or not always doable. we can replace the model above with simulations that we run ourselves. The problem with radiation transport is that our equation is very expensive to solve. So statistical methods or deterministic methods, they're way too slow to be put into an inference engine. So we have to use surrogate models or reduce order models. This is what will be able to update the simulation engine of the digital twin on a reasonable time frame. The Monte Carlo deterministic methods can take hours to run. So you're not going to do an inference in near real time if the simulation engine is that slow. So we've already have an experimental data-driven source localization inference engine that we can put in the digital twin, and I'll show you a video of this in a few seconds. What you can take out from those pictures, we have detectors and in 4 glove boxes. The inference engine can tell you the most probable location from those different detectors where the source is, and we combine all the detectors, you find out exactly where the source is placed in any of those 4 glove boxes. But we want to supplement, as I said earlier, we want to supplement experimental data-driven surrogate models with simulation data. So we need to solve the radiation transport equation to do this. The problem with the radiation transport equation is that it is a very expensive equation to solve. I'm not going to go to the detail of the equation itself, but it is just very expensive to solve because the solution doesn't live in a 3-dimensional phase space. It lives in a 6-dimensional phase space. So it's a high-dimensional phase space equation that makes it quite expensive to solve. So we need to know the solution as a function of space, 3 variables as a function of energy, 1 more variable as a function of direction of motion, 2 more variables, so 6 variables. When you need to discretize an equation in 6-dimensional space, it doesn't take long when you discretize physical space, energy intervals, and the angle on the unit sphere. It doesn't take long for your discretization to reach many billions of unknown. My students run quite frequently 100 billion unknown problems. We reach trillion quite frequently. So it's not possible to put that simulation engine in the digital twin. So the Boltzmann simulation models are way too expensive and do not meet our needs. We have multi-query problems all the time because the inference engine is constantly asking, where are the sources? Where are the sources? What if the sources are here? What should we expect for detector count rate? So we have multi-query problems, and it's impossible to do this with the radiation transport code. So we need much faster surrogate models. I won't go into the details of necessarily reduced order models, but this is what we're using as a replacement for the simulation engine in the digital twin. We're basically using a non-intrusive model order reduction based on Gaussian processes, and we infer a good subspace. We learn a good subspace where the solutions of our problems can be found through a method of snapshots. And in the essence of time, I won't go into those details because those are more model order reduction techniques. But the key message is that we use reduced order models as simulation engines, and they can basically reach quite competitive computational time. So in the essence of time, I'll skip over a few things about reduced order model, how we do this, and maybe just highlight a 3D simulation that we have done. Here, we have a full order solution that takes, on the left-hand side, takes 30 minutes on 16 processor, 16 cores, and the predictive error is extremely small. You can see this on the bar, on the color bar for the error on the right. It's really small, and this runs in 5 milliseconds on a laptop. So key message is model order reduction can provide very fast surrogate models that can be put into an inference engine. And the inference engine is what we have the digital twin working on. So since I have 1 or 2 minutes left, I'll finish from how we go from model order reduction to the digital twin. So we have an inference engine that runs really fast that tells us where the sources may be given some sensor data. The sensor data are the 16 detectors in our 4 glove boxes. The inference engine uses a reduced order model here. The reduced order model is, of course, built on a full simulation models that we've done offline. So we've learned the active subspace in which the parametric solution lives, and the inference engine therefore only needs to use a reduced order model. There may be other additional functionalities that you can do, like if the inference engine is having troubles, you can always request the full order model, let's say overnight or over the weekend, to generate a few more snapshots to help clear out some issues. And I'm going to conclude with a short movie of the room that I've shown you so far. And towards the end of the movie, we will basically turn on the inference engine, and with our current model, it will be able to tell you. I hope the video plays. Yes. I hope it's not too choppy. And towards the end, you will see that the simulation engine will actually be able to tell you, hey, I found a source and it's likely there. So the source, and I know the answer is where the green dot is, the green cylinder is currently, but the inference engine that lives with the digital twin will be able to tell you, hey, you likely have a source in this location. So our path forward, and I'll conclude on this, is in addition to a surrogate model based on experimental data, we want to include simulation-based reduced order models in our digital twin, and we want to use augmented reality and virtual reality to have a more 3D interactive visualization of what's going on. And again, this is about 5 weeks of into this new project. So small apologies if I've been only able to show you 5 weeks of work, but if anybody wants to reach out and know more about how we do things, I'll be more than happy to talk with anyone. And with this, I return the floor to the chairman.
Yeah, thank you so much. It's very interesting. So do you have any questions from the audience? Anyone? So John, this facility is at Los Alamos, right?
That's correct.
So you mentioned about the VR and development. Do you have anyone from Los Alamos to help you, or you have someone here to help you with that, the AR, no, VR application?
The augmented reality was done by Ian Halvik. He has some knowledge on how to do this.
I see.
Graduate student here in Halvik did all of this. We try to do a little bit of everything, augmented reality, reduce order models, full order models. So we're a little bit jack of all trades, but if we're doing something, not the most modern way or the most appropriate way, if anybody wants to reach out to us and say, you can do it differently, we know the tools, you can do this more quickly, I'd be more than happy to have people, work with us or just interact with us on possible other directions. But currently, this is what we're doing.
Sure. Ulysses, do you have any questions? Ulysses, I saw you are unmuted. Do you want to ask any questions?
And I think I forgot to turn my video back on, sorry. Sorry.
Yeah, I would like to ask a question. Can you hear me now?
Yes.
Yes, go ahead.
Yes, sorry. So thanks, Jean, for your talk. I wasn't aware of this project. Very interesting. So, you know, the radiative transfer equation seems to be an ideal model to apply, you know, physics-informed machine learning, right? Because it's 7-dimensional. You said 6, but in some cases 7-dimensional. And like you said, you cannot build this. You cannot build meshes. It's impossible. So this I just wanted to. It's more like a comment than a question. It's very good ground for developing these surrogate models based on physics-informed neural networks, Gaussian processes.
Yeah, let me just show you why we're still going with the maybe a more classical method of snapshot, and then discovering the subspace that we should be using for a parametric family of solution. And here the parameter is where the sources are, where do they move in the glove boxes. So we obtain a bunch of solutions that are parameterized with source position, if you want. And then we learn from that from the snapshots. We learn the subspace, we compress it, and then we only need to learn the how to seek a solution in that learned subspace. Because usually a facility is fixed in terms of its layout. The glove boxes will always be where they are. The facility may live for 15 years. A room may be unchanged for many years. It could be possible that the method of snapshot and maybe learning with a Gaussian process regressor, the family of solution, may be just good enough. But I agree that physics-informed machine learning could also be. I mean, we're already using Gaussian process. Maybe we can still categorize this in one way or the other as being under the framework of machine learning. But yeah, I fully agree that investigation of things like pins would be also of value.
Yeah, but that is exactly the point. I mean, if you have the snapshots, you can add that to the physics to get a much more accurate prediction than just using the snapshots. Like a Gaussian process,
yeah,
like a standard Gaussian process will not give you the same accuracy as a physics-informed Gaussian process.
And the good thing with pins is that you can both incorporate your simulation model and your measurement data as well. So
exactly.
There are things that are difficult to model. What's in the wall? Do we have water line for maybe restrooms, and neutrons that like to bounce on very light elements. So how far do you push the model? And sometimes the simulation model becomes very complicated. But if you have some experimental data that you can bring in with your simulation model, and pins lets you do this quite easily, it could be the best of both worlds.
That would be a great proof of principle.
Yeah. Okay, that's great.